Hi, this video is about Fermi-orbital descriptors, in specific their interpretation in a chemical bonding picture. Regarding what FODs are, in our recent video, which deals with the introduction to the FLO-SIC code, we gave the mathematical background to what FODs are and what the corresponding localized orbitals are. So if you haven't seen this video, you should do this right now and then come back to this video. The link for the video explaining what FODs are can be found in the video description here. Right now, we are more focused on the interpretation of these FODs in a chemical bonding picture, and it turns out that these FODs can be interpreted in terms of single, double, or triple bonds, or even other bonding configurations, as well as lone pairs. For example, here on the right hand side we have ethanol, C2H6O, where in brown we have the carbon atoms, in white the hydrogen atoms, and in red the oxygen atom. In addition, the green points correspond to the FOD positions of one spin channel. The FODs of the other spin channel are at the same position. As we can see, there is one pair of up and down FODs between all carbons and all hydrogens, as well as between the oxygen and the hydrogen. These now correspond to single bond orbitals, and with that we characterize these FODs as single bond FODs. In addition, we see that between the two carbon atoms and between the carbon and the oxygen, we also have one pair of FODs, one for each spin channel, and we characterize these as single bond FODs, which correspond to the single bond orbitals between these atoms. In addition, we see that on the oxygen we have two pairs of up and down FODs that are not in a bonded region, which correspond to the two lone pairs which reside on the oxygen atom. In summary, we see that the FODs give a picture of the chemical bonding as well as on the lone pairs, and as you can see, these FODs arrange in tetrahedra throughout this entire molecule. This discussion can be generalized in terms of an FOD bond order. We can derive this bond order by counting the FODs, or correspondingly the orbitals or electrons, in between atoms, and then divide that by the number of atoms which correspond to these FODs. To illustrate this a little further, we have another example over here. This is caffeine, where in addition to the carbons in brown, the hydrogens in white, and the oxygen in red, we have the nitrogen in bright blue. As we can see, there are several situations where we have a single pair of up and down FODs in between atoms, which corresponding to our FOD bond order means we have two FODs, one of each spin channel, over two centers. And with that we divide 2 by 2 and get a bond order of 1, which is exactly the single bond that we find. On the other hand, there are situations where we have two pairs of up and down FODs in between two atoms, which again means we have 4 FODs, 2 of each spin channel, divided by 2 centers, which gives us a bond order of 2, corresponding to the double bond nature in between these two atoms. We can generalize this to any bond order that you will find, and with that the FODs correspond to the chemical bonding picture in a given molecule. Also, as mentioned before, the FODs always tend to arrange in tetrahedra around atoms. Given that for every FLO-SIC calculation we have to optimize the FOD positions, we need to initialize them first. And I would like to present 4 modular FOD generators that are all freely available at the PyFLO-SIC organization at GitHub. There is the FOD-MC, which is a Monte Carlo based FOD generator based on the minimization of Coulomb repulsion while maintaining a given bond order. There's PyCom, which is the Python-based center of mass, which takes the localized orbitals and computes their center of mass as starting points for the FODs. PyEFF is a Python-based electron force field in which the electrons are treated as classical electron positions and are then moved within the force field formulation. And PyLewis effectively combines knowledge from previous experience, that is, structural motifs for certain bond arrangements or lone pair arrangements, to then initialize these structural motifs into a given molecule. With that, I'd like you to stay tuned. The OpenSIC project is at Twitter, where we update news regarding this project. We are at ResearchGate, as well as on YouTube, where we will upload videos like this one. And with that, I would like to thank you very much for your attention.